Oh no, sorry about
Okay.
that.
Yeah, it's fine. I saw the notes.
Okay, very good.
Yeah.
All right, so let's begin. I hope you can see my share screen here. So today we are kind of going to do some fun stuff, sort of like a continuation of last time. And we're going to look at this problem, this general problem of, quadratic optimization over the hypercube. And so, oh, actually, before we talk about this super fun stuff, let me, make an announcement because I'll forget otherwise. So the announcement is that there's a cool workshop uh, at Simons Institute in Berkeley, and there's a link to that. There's a link for registering for that posted on Diderot. Um, the workshop is not, of course, all about sum of squares, but a lot of the talks are going to be about sum of squares. But also the rest of the stuff, which is not about SOS, is also a lot of fun. And you can just get the it's all online, so you can get Zoom links for it just by registering. So I recommend doing that. It's all of next week. Okay, so all right, so let's study quadratic optimization over the hypercube. So last time, we saw the Gomans-Williamson algorithm for max cut. Recall that that was the problem of maximizing over the Boolean hypercube, this quadratic polynomial fg of x. And towards the end of the class, I in fact explained to you that this polynomial can simply be written as, you know, quadratic form of a matrix associated with the graph. And we call this matrix the Laplacian matrix of the graph. So LG is the Laplacian matrix. And if you don't recall what that is, you can check that this fg of x equals x transpose L sub g of x holds for the following matrix. It's D minus the adjacency matrix. So this is the usual, 0, 1 adjacency matrix of the graph. And this capital D is the diagonal matrix with, the degrees of the vertices written on it, written on the diagonal. Okay. And so we saw that, this problem of maximizing fg of x is basically, the problem of maximizing the quadratic form of this Laplacian matrix. And one thing you might remember, and we'll kind of get back to it again today, is that this Laplacian matrix is always, positive semi-definite for all possible graphs. And so, this is kind of nice. And the reason I'm recalling this, at least in this Laplacian way, is because, you know, all we saw was, the problem of optimizing a certain homogeneous quadratic polynomial. And all homogeneous quadratic polynomials can be written as quadratic forms of some matrix. So they can always be written as x transpose bx for some matrix B. And so what we're going to do today is basically, study, uh, in some sense, vast generalizations of the max cut problem to optimizing, any input quadratic polynomial. Okay. So that's our goal. But before doing that, I kind of want to, make one comment about the stuff we did the last time. This is just, so this could be somewhat boring because I'm kind of rehashing what we already did, but it's kind of nice to, make sure that these basic points are clear before we move on ahead to this general question of quadratic optimization. Okay. So last time, so this is still, last time continued. We looked at this question of max cut, and we stated the main result as the existence of a degree 2 sum of squares certificate, right? But really, we proved that there is a degree 2 sum of squares certificate for a certain, relaxation of this cut polynomial by actually giving a so-called rounding algorithm, right? And if you recall what that rounding algorithm was, um, then it looked like, so the rounding algorithm, did the following. We had this pseudo distribution, which we kind of assume by duality that we can work with to prove the certificate existence theorem. So, we took this pseudo distribution over plus minus 1 to the n. We said, without loss of generality, we can assume that the expectation of the linear vector valued polynomial x has to be 0 under mu. This is because we can symmetrize mu. We can consider the following, operation where, you draw x from mu and, output plus and minus x uniformly at random. And that corresponds to the simple operation of simply setting the mean of, the new pseudo distribution to be 0. And the covariance of the new pseudo distribution equals the second moment of the original pseudo distribution. So if all of these were too many words for you, all I'm saying is that, you can assume that, E mu x is 0, and you are given E mu xx transpose, which also equals the covariance matrix of this pseudo distribution. Okay, so we were given this pseudo distribution and we said, okay, all we're going to do is just select a Gaussian vector with 0 mean and covariance xx transposed, and simply set x hat I, which is our rounded vector, to be, the sign of gi for every I. And in fact, we're going to use the notation that x hat, the vector, is sign of g, where sign is applied entry-wise. Okay, so this is the algorithm, rounding algorithm we analyzed. And, we observed that in fact, one could think of this as simply an algorithm to solve the problem of approximate max cut, right? This could simply be understood as an algorithm to find, a cut which is, approximately maximum. I want to maybe make a couple comments about that because it's an important way to think about this issue. Even though, we will continue to think about certificates all along. It's good to think about, what are the ingredients that we didn't really go into detail about, but are important in, when you think of it as an algorithm. Good. So, so let's suppose you want to think of this as an algorithm. Then what would you do? Well, here is, you can think of the whole thing as a standalone algorithm, okay, without ever thinking about certificates, even though of course it's equivalent. Say, find a pseudo distribution of degree 2 mu that maximizes E mu of fgx, and find, or basically apply the above rounding algorithm. Apply above rounding algorithm. So this is the natural way to write this algorithm if you didn't care about certificates. And I guess I just want to, this is just basically a cautionary tale that, we didn't really analyze this algorithm in all the details. And I'm not going to do that, but I want to point out, the issues that underlie this, just so that, you don't take it super lightly. We'll take it somewhat lightly, but not super lightly. Okay, so what about the first step? Can we actually compute such a pseudo distribution? So we saw, in some sense, we actually can't quite compute a pseudo distribution maximizing a linear function in, pseudo moments of mu like this, but we can in fact, do it approximately. So, this kind of step is going to be okay. Let's maybe use yellow to point this out. So, we can definitely get something, we can get some pseudo distribution, which is, is at least max over all pseudo distributions fgx minus some epsilon, which, for polynomial time algorithms, we can in fact take it as just 2 to the minus n, just so that I don't carry around an extra parameter, right? So by the ellipsoid algorithm that we discussed the last time, and this Greshel-Lowasz-Schreiber framework, we can get something which is, approximately maximum up to this additive tiny error of 2 to the minus n. Okay, good. So this step is algorithmic. What about the rounding algorithm? So what does the rounding algorithm do? Well, it has to select this Gaussian. So we'll think about that in a second. And after you select this Gaussian, you have to, take its sign. So this step is easy. We can certainly, once we have a Gaussian vector or some vector, we can definitely take its sign quite easily. And so I guess the other worrisome point about this implementation of this algorithm is how are you going to sample this Gaussian? And Just I guess, I'm just going to give you pointers, not going to prove anything here. But the first observation is that if I have the ability to sample, so, let's write in yellow. Suppose I know how to sample a standard Gaussian vector, meaning suppose I knew how to, mm, draw a sample from a Gaussian with mean zero and covariance identity, then I can kind of simulate this a step of sampling a Gaussian with an arbitrary covariance. And what's the idea? Well, if I want to sample a Gaussian with, let's say, covariance sigma, then on your homework zero, which it's never ending, we're going to keep referring to homework zero at least a few more times in few more upcoming lectures. So in one of the things that you did in the homework zero, we kind of hinted at this operation of taking square roots of PSD matrices. Every PSD matrix can be written as sigma half transpose, sorry, I guess. And because it's a symmetric matrix, I can simply, in fact, call it square of sigma half, where sigma to the half is simply notation here. It's what we call as the square root of PSD matrix. And we didn't quite define square roots, but we proved that, in fact, every PSD matrix can be written in this form. And so what we can do then is sample a Gaussian from identity covariance and mean zero, and then simply set G to be sigma to the half H. And again, one of the things you proved on homework zero was, how to calculate the distribution of this new Gaussian. And it's kind of simple to show that its mean is still zero and its covariance is going to be sigma. Okay, good. So that tells us that it's okay to just focus on, the task of sampling from standard Gaussian. And now this is kind of tricky. Okay, this gets into the issues of, whether you have actual randomness, whether you have pure randomness that you can access. And even if you can access purely random bits, how do you sample from continuous distributions? And these are all non-trivial questions. And as you can imagine, we can only approximate these kind of things. We can obviously, never on our computers generate a truly Gaussian sample. But there are ways to get, arbitrarily good approximations in the relevant sense. And I won't discuss that, but if you're interested, check out the Box-Muller transform, which is like one way to do this. And once you replace all the sampling steps by approximations, you have to go back and look at the analyses where we're using Gaussianity, and make sure that those kind of things work out even when things are only approximately Gaussian. And so, for example, we had the Shepard's lemma that we proved the last time. We now have to prove it for approximate Gaussians in a relevant sense. Again, none of these are sticking points. They all work out. But I just want to point out that when you're designing algorithms, in the Turing machine model, more needs to be done. What we discussed was not an algorithm. It was kind of an outline of an algorithm. Okay, with that said, in this class, we are really, focused on the high level issues. We are not interested in, or we are at least, not specializing in the low level issues of the sort that we just discussed. So even though I sketched this out to you, I will not, do this kind of analysis in detail. I'll just claim that they can be done. And, I will point out some resources on Diderot for you to look at in case you're interested. And things are going to get hairier from now on. So, the details of implementation could, get a little bit more complicated. But, all of those things are going to work out, and all of these things can be worked out. And in your notes, I'll always point out in the polished version of the notes, I'll always point out, these kind of things explicitly. Good. So with that, pedagogical, important, but somewhat boring note, squared away, we can come back and really call what we discussed an algorithm. Find a degree 2 pseudo distribution mu that maximizes this degree 2 polynomial, the expectation of the degree 2 polynomial, and apply this Gaussian rounding algorithm, which is simply select a Gaussian with the covariance e tilde mu of xx transposed, take the sign of the vector. Okay, that's the algorithm we analyzed. And coming back, for this class, we are looking at this as an example of quadratic optimization, more precisely homogeneous quadratic optimization.
Pravesh, quick question.
Yeah.
So Raj just asked if there's like a deterministic algorithm for max cut with also.
Good. It is a great question. And actually, this algorithm can essentially be de-randomized. So there is, in fact, this is an important point. So let me, maybe repeat it and make a comment about it. So Raj asked the intriguing question. So our rounding algorithm was randomized. So the task of computing a pseudo distribution is certainly, we can do it with a deterministic algorithm, because ellipsoid, can be run via deterministic procedure. But our rounding algorithm was randomized, right? We had to choose a Gaussian, and that certainly requires random bits. And in fact, we glossed over the whole issue of, where are these random bits coming from, etc. But all of these issues go away if we simply just focus on designing deterministic algorithms. So you could really ask, can I de-randomize this algorithm? Can I somehow, implement it without any access to any kind of random bits? And it turns out you can. And, you need certain notions of, okay, let me just use a buzzword. It's called a pseudo-random projection. And, there are ways to, deterministically sample matrices which pretend to be projection matrices, and they kind of behave like random projection matrices. And it turns out that, using those, we can actually implement this algorithm completely deterministically up to this 2 to the minus n loss that we have to incur anyway. This additive 2 to the minus n loss that I mentioned earlier. So the answer to Raj's question is yes. The way to prove it, yes, is interesting. But again, we will not do it. We'll be happy with randomized algorithms in this class. Okay, great. So coming back, we are interested in quadratic optimization today. We want to generalize this observation that we did for max cut the last time. And there's like a really cool theory. And so today I get to do some real cool operations on matrices and, design new rounding algorithms, which kind of look like the last time, but the analysis is still very interesting. And so it's going to be fun. Good. So recall the setting. If you were sleeping through what I was just saying, or, if you ignored, come back, because everything is going to, refresh now. So your input is a matrix. Okay, and it's going to be an n by n matrix. I'm calling it over the reals, but really remember, these are inputs over algorithms. So, they live in rationals, right? And because, we have to measure their bit complexity, etc., we always think of the inputs as over rationals. So we are, we have an n by n rational matrix. Our goal is to, approximately solve this quadratic optimization problem. Okay. And I explained to you why, what we did the last time was a special case of this. It was a special case where B was the Laplacian matrix of the input graph. Okay. But we want to discuss this problem in detail now. We want to see, what can we do about this very basic question, right? Good. So we're going to, prove some cool results. I want to give you some, highlights just to, keep you awake. We're going to show, so, remember I said that L sub G is the Laplacian matrix of a graph, and in particular, it's always positive semi-definite. So one thing you could ask is, well, what if B is an arbitrary positive semi-definite matrix? Can I somehow, do the same rounding and get some non-trivial, approximation factor? The answer is yes. And it's like this really beautiful theorem of Nesterov that we're going to prove today. It's a very simple proof, but we'll do it in detail. And so the case we'll start with, it introduces us to like the first main tool that we'll use to prove this Schur product theorem. So we'll, use this and prove this Nesterov's theorem, which proves that when B is PSD, we can in fact get a pi over 2 approximation. So, pi over 2 is about 1.5. So it's not too bad, right? Like we can basically approximate the maximum over the hypercube of X transpose BX for any PSD matrix B within a factor of about 1.5. Okay. And this is a result of Nesterov from the 90s. So, basically after Gomans and Williamson discovered this algorithm in 94, there was kind of an arms race between all the optimization biggies, and all these results basically came in swift flows. So Nesterov discovered the pi by 2 theorem. This result goes by the name of pi by 2 theorem, which we'll prove today. And then there was this line of work which was begun by Noga Alon, and Asaf Naor. And they realized that there is kind of a nice behavior of this optimization problem, which you can characterize in terms of the support of the matrix B. So support of the matrix B is basically, the pairs I comma j where the entries are non-zero. Okay, so this is basically the set of all, we always think of symmetric matrices. So if ij is non-zero, then so is ji. And so it's a set of all ij's such that bij is non-zero. And what Alon and Naur observed, and actually we'll do this part also in detail today, is that when support of B is a bipartite graph, then in fact, even if B is not positive semi-definite, as long as the non-zero entries of B form a bipartite graph, you can again get a fixed constant factor approximation. Constant factor approximation, believe it or not, what constant it is a huge open question even now. I will prove to you that this constant is at most 1.748 something, but it's already known that it's not tight. The proof I'm going to give you, it's already known that it's not tight. And it relates to this very famous and basic functional analytic inequality of Grothendieck. So we are actually, going to prove, what is called as Grothendieck's inequality. We're going to give an algorithmic proof of that. And in fact, we are going to give a proof due to Krivine from 77. That gives like a non-trivial constant upper bound, but it's not tight. We already know it's not tight. So we'll do this. And then, towards the end of the class, we'll go to the most general setting. What if we don't know anything about B? What can we say about completely arbitrary Bs? And let me keep the approximation factor that I'm going to prove to you for this a secret. We'll get to that, once we reach the end of the class. That's one strong motivation for why you should hang around, in the second half. Good. All right, so let's begin. So we'll start with this famous result of Nesterov. We'll prove the Nesterov's pi by 2 theorem now. So let's write down the theorem statement to begin with. So let B be a positive semi-definite matrix. Then opt of B over C minus X transpose BX has a degree 2 SOS certificate for C equals 2 over pi, which is about 0.63. Okay. And in the spirit of making it equivalent to this algorithm that we just discussed at the beginning of this class, let me also say that we can basically equivalently say from our proof that given a pseudo distribution of degree 2, let's say mu, we can actually efficiently sample from a distribution x hat such that x hat transpose b x hat is at least 2 over pi minus 2 to the minus n tilde e mu x transpose bx. So, we can get essentially 2 over pi fraction of the objective value that the SDP was giving us in polynomial time. So that's what I meant by efficiently. Good. So are there any questions so far before I go on to prove this theorem? This is just so that, I get a chance to drink some water. All right, no questions. Everything is excellently clear. We won't stay that way for long. So, our rounding for proving this theorem is going to be exactly the same as last time. Okay, we are just going to do Gaussian rounding. we'll just analyze it, more cleverly. So what's our rounding? Recall. We're going to choose Gaussian from the same which has the same first and second moments of the pseudo distribution, and recall that we can assume that the mean of the distribution is 0 by symmetrization, just like the last time. So we're going to choose a Gaussian with the same second moment. Second moment is the covariance. And we're going to choose the rounded distribution to simply be the sign. Okay, for all 1 less I less n. Good. So let's analyze this. Let's see what happens, okay? So the analysis, as you can imagine, because it's literally the same rounding, has to, depend on Shepard's lemma. So let me remind you of that. We saw it last week, but one downside of like once a week class is that we can forget things. So recall, here's what we proved the last time. It was a completely simple two-dimensional geometric argument. The probability that this sign rounded x hat, if I look at let's say the values for any pair of coordinates I and j, the chance that they are different equals arc cosine of the expectation of the Gaussians we began with over pi. Okay. Last time, and I introduced this extra row, etc. Today, I'm not going to do anything with that row, so I'm just gonna, not introduce extra notation. So if you don't recall the proof, let me, quickly remind you, because it's really, really simple. So, you should feel like you know all that I'm talking about right now. So remember, we said, because of how nice Gaussians are, we can always assume that GI is, h dot v and GJ is h dot w, for h being, standard Gaussian random variable in, 2 dimensions. So we can always think of, our correlated Gaussians as, projections of a 2-dimensional standard Gaussian. And the way we encode the covariance structure of G's is, we force some geometry between V and W. So we know that V and W must be norm 1. This is because EGI and EGJ square has to be 1. And in order to capture that E of GI times GJ is, whatever we want it to be, we're going to set V dot W, the inner product, to be expectation of EGI GJ. Good. So last time we discussed why this can be done. And then the way to analyze it is very simple. The probability that well, left no space for myself there. So probability that sine of GI is different from sine of GJ. It's the task of asking the probability that I choose a random Gaussian H that kind of falls in between V and W when you put them on the circle. Remember, we drew this diagram, this nice diagram. V, W, and it's basically asking for the probability that H looks like this. That's when sine of V dot H and W dot H will be different. And we can state that because of rotational invariance of Gaussian, we can state that very simply. If this angle is this angle is arc cosine of rho, because arc cosine of EGI GJ, because V and W have that inner product. And that's the same angle here. So basically the sum of these two angles over 2 pi is the probability. And that's, exactly what I quoted above. This is arc cosine EGI GJ over pi. Okay, that was a quick refresher of what we did the last time. And so one thing I want you to now, observe is that because today we are going to, today we are doing this general quadratic optimization. So I want to just rephrase this observation, the Shepard's lemma, in terms of, what happens to the degree 2 correlation between the rounded variables. So here is like an equivalent proposition. Really, it's a corollary that E x hat I, x hat j equals 2 over pi arc sine of E gi gj. Okay, that's what I want to prove to you. It's very simple. I'm just going to compute based on the Shepard's lemma. So let's compute this, okay? So here is a quick proof. So, since x hat I and x hat j are plus or minus 1 valued, I just have to, I can just simply write it like this, equals. So what's the chance that take the value -1? Well, that's what we just computed. We just computed the chance that they are different. When x hat I and x hat j are different, their product takes the value -1. And the probability we said was going to be arc cosine EGIGJ over pi. And then with the rest of the probability, they must be equal, in which case the product is exactly equal to 1. So I can write it as 1 times 1 minus the same expression here. Okay. So now if you do simple math, then you get that this correlation equals 1 minus 2 arc cosine of EGIGJ over pi. And now I'm going to use elementary trigonometry to confirm that this is pi over 2 arc cosine. Actually, I haven't used trigonometry yet, but I'm soon going to. So pi over 2 minus arc cosine of any angle is actually equal to arc sine of the same angle. So you see that really was my goal. Okay, that's a neat expression for, what happens to correlations of these rounded x hats, pairwise correlations of the rounded x hats. Okay. So okay, I guess I'm just refreshing, so you don't need to stop for questions here. I'll write this cool lemma and then stop for questions. So here's the cool lemma that that is behind, what Nesterov did, and really, in some sense, would be behind essentially everything we proved today. Okay, it's a very simple, very elementary linear algebraic observation, but once you make it, things just work out beautifully. So here's the cool lemma: let M be positive semi-definite, and let's say that diagonals of M are going to be 1. So they're all ones, okay? And these should not surprise you. These are the kind of matrices that, we are living and breathing for both last time and this time. So, we really like these matrices. We do work with them. So let M be a PSD matrix with diagonals 1, okay? So let F be any function of a single variable. Then, for any function F, I'm going to now describe a new matrix which somehow uses F, okay? And because this is a weird, funky operation to do on matrix, I'm going to use a weird, funky notation. I'm going to write this as F square bracket M. Okay. Not to be confused with F round brackets M. Okay. And what does this mean? So it's also going to be a matrix. If M is a small n by small n matrix, then so is going to be F square bracket M. And it's just obtained by applying this function F entry-wise to the entries of M. Okay, so F square bracket M, the ijth entry, is simply going to be F of Mij. Okay, so I'm just going to apply this univariate function entry-wise to M. Okay, good. So now, I have like some function that takes matrices to matrices. And here's like a weird fact that, a priori, if you think of M in terms of its eigenvalues and think of it as operators, it looks very, very funky, but, we're going to prove this as a very simple proof. So suppose F has a positive coefficient Taylor series that's uniformly convergent in the interval -1, 1. Okay, forget about the we're going to need this infinite series one, but just think of it as a polynomial for now, okay? Think of it as a F being a polynomial with non-negative coefficients. So F is a univariate polynomial where each of its coefficients are non-negative. Suppose that's true. Then F square bracket M is also PSD. Okay, I'm going to pause for effect and questions. Okay, so I guess it's a weird statement, but we're going to prove it. Are there any questions?
Yeah, so quick question. Is this related to Schoenberg's criteria where you show that like all positive semi-definite functions applied to a set of Euclidean distances remain Euclidean?
I have to say I don't know what Schoenberg criteria is, but let's come back to that at the end. We
Okay.
have a chat session at the end, so we'll discuss this too. Okay, one of the cool things is that we have a super diverse talent amongst the people who are attending this class. So we can actually learn a lot more than what I can just pontificate. So we'll let Anish speak for 5 minutes at the end and tell us about Schoenberg something. Okay, very good. So we're gonna prove this cool lemma by proving a simple observation that Isai Shur made. 17th century mathematician. It's very, very simple. It says the following. Suppose M and M prime are PSD matrices. Then I'm going to define, if you haven't seen this before, it's this new way to multiply matrices. And actually, when I hadn't taken linear algebra, when I did not know, what to do, what's the right way to multiply matrices, I thought this would have been the right way to multiply matrices. Of course, we know it's not the right way now. We have a cooler way to multiply matrices. But if you hadn't taken linear algebra, here's what you might do to multiply two matrices. Just take the matrices, make them equal in dimensions, and just multiply them entry-wise. Okay? We know that this is a much less interesting product than the product that we are used to, but that's the one that we're going to focus on right now. So it's this, I'm going to denote this new product by M circle M prime. Some people call it the Hadamard product too. I actually don't know the history of this. So again, if someone knows, we can talk about it later. But if you take this entry-wise product, so, just to make sure that we are on the same page here, M circle M prime of ij is just product of Mij and M prime ij. Then, this M circle M prime is also going to be PSD. If M and M prime are PSD, then their Hadamard product is PSD. Okay. Before we prove this, it has like a really simple linear algebraic proof. But before we prove this, let's make sure that you see why it implies the cool lemma above. Okay. So how would we prove cool lemma? Proof of cool lemma. So, let's apply the Schur product theorem where M and M prime are both equal to M. Okay. And let's give this a nice name. Let's call this bracket M squared. Really, truly speaking, if I had to follow my notation from before, I should have said this is square of bracket M, but this is a lot easier. So I'm going to call it that. So this, is just M circle M. Okay. Now M and M are both PSD. So Schur product theorem says that this square bracket M square must be PSD. Correct? And in particular, I can repeat this argument now iteratively to get that for all positive integers I, square bracket M to the I is PSD, right? Good. And now I'm just going to use the fact that PSD matrices form a cone. So any non-negative combination of M to the I must also be PSD. Okay. And notice that this is same as taking the polynomial sum ci x to the I and applying it to M. So that's the proof of the cool lemma for polynomials. And now you can imagine that as if I have an infinite series that is uniformly convergent in the interval -1, 1, then I can actually apply it to not just polynomials but also this infinite series, because limits of PSD matrices are PSD. And so I'm just going to say QED here. Any questions? Good. So, okay, that was simple. So let's prove the Schur product theorem. And for that, we're again going to use something that you proved on homework 0. So you remember that if M is, so any PSD matrix can be written as some lambda I vi transpose for lambda i's which are non-negative. So let's say I have these representations for M and M prime. Then I'm just going to build a representation for M circle M prime and complete the proof. And so notice that if I just use linearity of the Hadamard product, which is easily seen to be linear, then I just have to take the Hadamard product of these rank 1 terms, and then lo and behold, I can just rearrange this. Sorry, this is J. Rearrange this to say Vi circle Vj prime. Okay, no, wait. This is really a circle. This is a dot. Vi circle Vj prime transposed. Where, as you can imagine, the circle is the Hadamard product of vectors, entry-wise product of vectors. Okay, that's it. I basically gave you a non-negative, a rank 1 decomposition of M circle M prime. This implies that M circle M prime is positive semi-definite QED. Good. So we are done. We are done with the proof of the cool lemma. So let's go and recall what the cool lemma was. The cool lemma said that if you have a univariate, polynomial, or in fact, more generally, a convergent infinite series, convergent in -1, 1, uniformly convergent, and let's say all of its coefficients were non-negative, then if you apply it entry-wise to a PSD matrix, apply this univariate function entry-wise to a PSD matrix, then in fact the resulting matrix must also be positive semi-definite. That's what we've learned. Good. So now we can go back to, wait. Okay, now we can go back to the proof of Nestero's pi/2 theorem. And the main way I'm going to use this cool lemma is the following corollary, which will be very familiar to you once I write it, or at least would look very relevant. So for the kind of PSD matrices that we like a lot, for M PSD with diagonals 1, if you apply entry-wise the function arc sine, then arc sine square bracket M must be must PSD dominate M. I guess I never formally defined this to you in homework 0. I'm sure most of you have seen this before. If not, all it means is that arc sine M minus M is positive semi-definite. Okay. The reason I can write it like this is because it turns out that it's a partial order on PSD matrices, and it's called the Lohner order. It's not important. We're not going to use anything fancy about it. Good. So why is this true? Well, in the light of the cool lemma, all I have to show is that arc sine M minus M, this function. So this, is, we're going to write it as, some infinite series applied to the matrix M. And we're going to observe that its coefficients are, non-negative. And I'm going to state, but, assume that you understand and agree that this infinite series is, uniformly convergent in -1, 1. And so that will be the proof. Okay. And, for that, I'm just going to, by fiat, declare the following infinite series that I checked from Wolfram alpha. This is just taking, terms 1 and beyond of the arc sine infinite series. So it turns out that it's like quite cool. It looks like, product of all odd integers. The kth term looks like product of all integers or all odd integers less than 2k. Something like this. I'm sure this is not super important, but it's so cool. So wanted to write it down. M to the 2k plus 1. And so the only observation is that these terms are non-negative. So we are done. Good. So we have proven. I don't know if this theorem would have, if this claim would have looked reasonable to you before this class. Like, I guess it's a really cool observation that Nesterov made. I think, even though it has like a very simple proof, it's a very cool observation that if you apply arc sign entry-wise to a PSD matrix with diagonals 1, then it's going to PSD dominate the matrix you began with. Good. And now, you can see where we are going with this. Now we can like complete the proof of Nesterov's theorem. So we already proved. So recall. So I guess this recall could have been done by just me scrolling upwards on the scribble, which you can do. But I'll just write it down again. That the rounded vector satisfies 2 over pi arc sine E G I G J. Okay, that's what we proved just using Shepard's lemma. And so what are we interested in? We are going to calculate the expected value, the expected objective value generated by this rounded distribution x hat, right? So let's try to write that down. So we are interested in x hat transposed b x hat, which equals sum over ij. Let's take expectations over x hat here, which equals sum bij okay, by using this consequence of Shepard's lemma. I can write it as 2 over pi arc sine E Gi Gj. And so now you see what my game is going to be. Just going to pull this 2 over pi out. Now, this equals, again, something that you did on your homework, the trace of the matrix B times the matrix arc sine EGG transposed, and these should be square brackets. So we already know, so now, so far, remember, we haven't used anything about PSDness of the matrix B, okay? And we basically, found a very nice expression for the expected value of the rounded quadratic form on B. And so now our observation is that if B is a PSD matrix, so here's like a simple observation. If B is a PSD matrix, okay, and C is a PSD matrix, then trace of B times C is non-negative. Okay, it's a very basic fact about the cone of positive semi-definite matrices. I forget if I asked you to prove this on the homework 0. If not, it has a very simple proof. I'm sure you can do it just using this rank 1 decomposition that we were using earlier. It's a very simple proof. And in fact, this has a nice name in geometry. It's called as self-duality of the PSD cone. And so all we're going to observe is that this guy here, so I can use the self-duality to conclude that 2 over pi trace of B times arc sine EGG transposed. Well, we already proved that this PSD dominates EGG transposed. So this must be non-negative. This claim implies this. And so that means that 2 over pi trace of B sorry, I'm not following my bracket hygiene here. Is at least 2 over pi trace of B E G G transposed. And notice that this because the Gaussian had the same second moments as our pseudo distribution, this actually equals 2 over pi tilde e mu x transpose bx. Yeah, that's it. And so, if you just, collect all what we did together here, we've proven that x hat b x hat equals 2 over pi So we've proven Nesterov's pivot 2 theorem. Okay. So now let's pause and take any questions.
I had a question.
Yes.
So I guess like if you're optimizing a quadratic form and the matrix is PSD, this doesn't really make sense. But is there like any sort of analogous like generic result about optimizing quadratic forms if you're trying to minimize instead of maximize?
Good. Let's see. Okay, so first I want to make a trivial comment. The trivial comment is that, the last result that we will prove today, it holds for every matrix B. And, just by making B minus B, you can minimize quadratic forms instead of maximizing them. Okay. But yeah, for a special class of matrices, I'm not sure I know of a meaningful result. I feel like there should be, but I guess I can't recall off the top of my head. In general, though, and maybe 2 classes from now, we'll look at higher degree variants of this problem. So instead of a quadratic optimization, how about a ternary optimization? How about a quartic optimization? All of those are relevant, interesting problems. They just turn out to be a lot harder than the quadratic case. But we'll see there that somehow the status of what we know about minimization problems versus maximization problems is kind of different. Yeah, I don't know if that helps you, but that's my uninformative answer.
Thanks.
More questions? Okay, so yeah, I mean, it's a really simple, elegant proof. I guess it's very easy to verify. And I guess not that confusing in terms of what's going on. So let's move on. What I want to do now, actually I want to change orders and do, okay. I want to change orders, and I actually, want to do the secret result I promised earlier. It's just like, I just realized that it fits my plans a little bit better. So we did the case of PSD matrices. So next up, we want to do the case where B is, basically an arbitrary n by n matrix. Okay, I know nothing about it. It's not PSD or anything. Let me take guesses. What do you think about this? What would be the best possible approximation we can get with degree 2 pseudo distributions for, optimizing quadratic forms of arbitrary matrices?
It's B is symmetric, right?
Yeah, that's kind of without loss of generality because you're optimizing quadratic forms. You're
Right,
optimizing X
sure.
transpose BX. So X transpose BX is same as X transpose symmetrization of BX.
Sure.
So yeah, B is, yeah, you can assume without loss of generality that it is symmetric. For example, anyone proposing that there is a constant factor approximation algorithm for this problem using degree 2 pseudo distributions? Who wants to bet $1,000? All right. So I don't know. The reason I'm building up so much is because, here I'm not going to be able to give you a constant factor approximation algorithm for this problem. And in fact, I'll give you something much weaker. I'll give you a log n factor approximation. And once I state the theorem, I'll also state, a yet another open question. But remember that I already given you one open question before, which is to basically, find a better rounding than, oh, I guess I haven't done that, but I just stated this Krivines rounding for the bipartite graphs. So I mentioned already one open question. We'll discuss that in more detail in the second part of the class. But here's like another open question for you, which is, find a better algorithm or prove that there isn't than the one that we're just going to see now. Okay. But before we do that, we kind of want to, I kind of want to like do something very basic and just understand, this problem of general quadratic optimization just a little bit better. Okay. So, so what are we interested in? We are interested in maximizing over plus minus 1 to the n X transpose BX. So I guess a priori, it's not even clear that the optimizer of the optimum value, so let's call this the value of this guy, let's call it opt of B. It's not even clear that opt of B is non-negative, right? B is completely arbitrary. B is not positive semi-definite. So it's not clear why, for example, if opt B should even be, non-negative. And why am I even asking that? Well, because, it kind of becomes important when I'm stating approximations as ratios, right? Like I'm giving you, multiplicative approximations to optima of these problems. Well, if the optima happens to be negative, then, the meaning of approximation ratio kind of completely flips around, right? And so for me to make sense of this, for me to keep talking about, approximation factors in a multiplicative sense, it kind of better hold true that opt of B is non-negative. Okay. So, so what we'll do is now, do some basic stuff that at least confirms this. It's all very simple. It just follows some homogeneity, but, I kind of want to just like make sure that we are all on the same page here. Okay. So the first observation I want to make about this problem, let's title this proposition as enough to optimize on the solid hypercube. Okay, instead of the corners of the hypercube plus minus 1 to the n, I'm actually now going to show you that in fact without loss of generality you can optimize on this larger set and really lose nothing. Okay, why is that? So let's state it the following way: let y be any vector in plus minus 1 to the n, then there exists a y hat in the corners of the hypercube such that y hat transposed b y hat is at least y transposed by. This is just true for all possible y's in the solid hypercube plus minus 1 to the n. Okay, so basically I'm going to prove to you that whatever you can achieve via any fractional point inside this hypercube, I'm going to be able to achieve the same value, or at least the same value with a point on the corner of the hypercube. Okay. Before proving this very simple proposition though, you agree that it immediately implies that opt of V is non-negative. Why is that? Well, if you take the vector y to be the 0 vector, which does live in the solid hypercube, then it achieves a value of 0. And so if I apply a proposition, then I know that, I can actually achieve at least that value also on the corners of the hypercube. Okay, so I'll just say choose y equals 0 and apply proposition. Okay, so that's good. So at least this proposition is somewhat helpful. So let's prove it. First, I want to say that I can assume that BII are all zeros. Wait. Actually, I'm going to modify my proposition. It's probably too strong right now. At least the proof I know doesn't work for it. I'm going to say that, I'm only going to prove it for, B whose diagonals are 0. Once I do the proof, I'll ask you if I needed this or not. But, let's assume.
No, I'm pretty sure you need this. I was feeling very confused because
Okay.
you can take B to be like minus identity, right? And this is just like all wrong.
Yeah.
If it's negative definite, then
It's over. Yeah.
Right. Okay, good. Yes. So I definitely need it. That clarifies things. So I'm going to assume diagonal B is 0. And I'll show you why it's not a big deal. So before doing that, let's make sure that we didn't bungle up the proof of this op B non-negative. So why can I assume? Okay, so okay, very good. So okay, so I guess it's not going to be true that opt of B is non-negative for all B. It's only going to be true in general for B's which are diagonal-less. Okay, so let's focus on diagonal-less matrices. Sorry about that. We're going to work with B which has no diagonals. Notice that the max cut thingy did not quite satisfy this. We had in this Laplacian matrix the diagonals were non-zero, but we kind of already saw that talking about approximation factors is weird if the maximum happens to be negative. And so in order to at least make sure that opt of B is non-negative, I'm going to work with diagonal B equals 0. Okay, good. Okay, so then you agree that corollary works. Well, because the proposition works. So now let's prove the proposition. Okay, so I guess in my notes I said can assume B sub II is 0, which is like trivially true. I don't need to assume. I assumed it globally. So what I'm going to do, I'm going to give a very simple proof. I'm just going to give you a distribution on plus minus 1 to the n, such that, so let's say this random variable is going to be y hat, such that e y hat I y hat j equals yi yj for all ij. Okay, that's what I'm going to give you. If for all I not equal to j, the diagonals are coming to bite me. For all I not j, the expectation of this Boolean valued vector y hat, the pairwise correlation of this Boolean valued vector y hat will match that of y. And so how would I do this? Like once you ask for this, obviously it's very easy. I'm gonna set yi to be the following random variable. It's going to be 1 with probability half plus yi by 2. So remember y, the entries of y are in the solid hypercube plus minus 1 to the n. So these numbers are at least kosher probabilities. Like yi is between plus minus 1, so half plus yi over 2 is between 0 and 1. So I can at least call them probabilities. And, with the remaining probability, which actually equals half minus yi over 2, I'm going to set, it to -1. And I'm going to do this independently for each, coordinate. Okay. So now what? Well, then E y hat I, y hat j equals, so now this expectation is over the random choices in defining y hat. Y we are assuming is fixed, equals E y hat I times E y hat j. And then, it simply equals, so what's the expectation of y hat I? Well, it's 1 with probability half plus yi over 2. And it's -1 with probability half minus yi over 2. So, that equals yi. That's it. So I just simply gave you a distribution which is on the hypercube, and its expectation equals y. Okay, so hopefully, this convinces you. So what does this imply? This implies that, expectation of y hat transposed b y hat equals y transpose by. Any questions? Actually, I just realized that I don't have to assume diagonal b equals 0. Like, in some sense, I want to say that without loss of any generality, I think I can assume that diagonals of b are, non-negative. So why do I say that? So I want to say that, if that's not true, let's say, for example, diagonals of b were all, less than 0, then the maximum can only be 0. Right, over the solid hypercube. So at least over the solid hypercube, over the +-1, the solid hypercube +-1 to the n, optimizing a negative diagonal matrix is going to be, simple. Anyway, so not totally sure if that carries over into the corners thingy, but there might be a way that we don't have to, make this diagonal 0 assumption, and we can make this result.
I'm not sure. I mean, I agree that if all the diagonals are negative, then you're fine. But if you have a mix of positive and negative, I think this is not.
Well,
fine.
over the solid hypercube, you can always take, I see, you're saying then, if you have a mix, then, you can always get a non-negative value, right? Because then you're supposed to just focus on the principal submatrix where you have positive entries. The non-trivial thing is only when the diagonals, are all negative.
I think it'll suffice for the trace to be positive, because then you just remove the diagonal, and you have by this probabilistic method, you have a +-1 thing that has positive inner product with the hollow matrix, right. And then when you multiply it by a diagonal matrix, you're just getting the squares on everything, so it's just the trace.
Right. Absolutely. Yeah. So that's a good point. Like, over the hypercube, the way I can state like a slightly more general result is by assuming that the trace of b is non-negative instead of diagonals b being 0. That's clearly enough, because then, I get like a strictly, the diagonals only contribute a non-negative term, then like a fixed non-negative term. It's a constant because over the hypercube, xi square are all 1. So I get the contribution of the diagonal remains n times the trace of b. Anyway, doesn't matter. Let's just continue with diagonals b equals 0. But there is some sense in which you can be slightly more general than that here.
Sorry,
okay.
Why can't you just take negative b if the opt is less than 0?
Because we said the problem. Yeah, because I started by setting the problem that I want to maximize x transpose bx.
Oh, okay.
Yeah, I mean, we could do lots of things if we start negotiating with the problem, but I suppose we fix the problem first. Anywho, okay, good. So, fun distraction, but at least we've convinced ourselves that if diagonals of b are 0, if the diagonal entries of b are 0, then opt of b is always non-negative. In fact, I'm going to use this in a second, so I'm going to observe this right away. I can give a non-trivial lower bound on opt of B for arbitrary B. I want to say that opt of B is always at least 1 over n, the sum of all absolute values of the entries of B. Okay, so in particular, if if the matrix is not all zeros, then this is a better lower bound than 0. Okay, and I'm going to need it in a second. So I want to just like do a very quick proof of this. And here's the idea. Again, I'm going to give you a randomized choice of points in the hypercube, which in expectation achieve the right-hand side as the value. And that's basically enough to prove that opt of B is large. And so what I'm going to do is, select random perfect matching of the complete graph. What does that mean? It means the following, okay? You can do it in the following way. Just like pick a random edge, pick a random pair I comma j, remove it from consideration. Now you have n minus 2 vertices left. Pick a random pair from the remaining vertices and continue so on. So at the end, you'll basically have, partition n. Okay, let's assume n is even. The odd actually doesn't matter. But let's say, for now, n is even. If n is even, I can just construct a perfect matching of the n vertices, right? And now what I'm going to do is, so I'm now going to give a distribution over assignments for each choice of this matching. So let's say I comma j is in the matching. So then, choose x hat I to be random, just uniformly random entry in plus minus 1. So one of the endpoints of this edge. So basically, what I'm trying to do is like I'm trying to get objective value contribution only from the pairs that I picked, only from the entries of B inside this matching. That's what I'm trying to do. Okay. So here's what here's how I'm going to accomplish that. I'm going to choose x hat I to be a random entry in plus minus 1. And then, I'm going to choose x hat j equal to x hat I if bij is bigger than 0, and make it if and only if. And so, in the other possibility, x hat j would just be negative of x hat I. Okay. So now let's understand what is happening to the value, to the value of the quadratic form. For every edge in the matching, because of how I chose the second endpoint of each edge, I have aligned x hat I, x hat j to have the same sign as bij for every edge in the matching, right? While let's see what happens if ij is not an edge in the matching. Well, in that case, remember x hat I is uniformly random. And so expectation, if ij is not in the matching, then E of x hat I, x hat j is 0. Right? That's simply because x hat I was chosen to be a uniformly random plus minus 1 valued random variable. Okay. So what does this mean? It means that x transpose b x hat is at least some, let's call qij, the 0, 1 indicator of whether the edge ij is in the matching. Then this proof has given us that expectation of x hat transpose b x hat is at least, the sum of the absolute values of entries of B that lie inside this matching. Okay. And now, all I'm going to observe is that the probability, because I chose the matching randomly, if I now take, expectations over Q, the probability that any edge is picked up in the matching is exactly equal to 1 over n when n is even. Actually, once you do this proof, you also see that n even doesn't matter. If n is odd, then in fact, I think every edge is picked with probability 1 over n minus 1, because there's no perfect matching. So each matching, in fact, only has n minus 1 edges, with n minus 1 over 2 edges. And so you can prove that every edge is picked with probability 1 over n minus 1, which is larger than 1 over n. And so in any case, this expectation is at least 1 over n sum ij absolute values of entries of B. Okay, so we got like a slightly non-trivial lower bound on the optimum of this quadratic optimization program. Good. So let's now do something slightly non-trivial. Actually, this is also going to be pretty easy, but it's the main theorem for this part. And this is going to happen to us yet again, I guess, bunch of times in this class. So, I told you, I guess in the first lecture that sum of squares and the associated SDPs were actually invented in multiple fields from like slightly different perspectives. And, it was not just that, many times actually the people working in these various fields were actually thinking about the same problem in disguise. And so what happened is that for some of the theorems, people proved it in like multiple ways, and people didn't realize that they were already proven. And so even though, this theorem appears in a very nice paper of Magretsky, which I was reading last night, and I posted on Twitter, it's an excellent, it's an excellent paper to read. It actually, was also reproven in a paper of Chariker and Wirth. I think maybe 5 years later or something. I forget if this is 2004 or 2005. It's a very simple result. So, there might be other, maybe some paper of Nesterov, which also did it somewhere. But basically, what I've definitely confirmed is that it's in Magretsky's 2001 paper. Okay, good. So here is what, the theorem is. So let n be large enough. So I think, 60 works if you carefully calculate constants, but I won't. Then for C equals order log n, again, I think C equals 4 work. Sorry, the constant can just be taken to be 4 log n, I think. But I won't do that. So let's say C is at most 4 log n. Then opt of B over C minus FB, which is just X transpose BX, has a degree 2 SOS certificate. Okay, and the same rounding business applies. So in fact, all our proofs will actually yield efficient rounding. So further, for all pseudo distributions mu on degree 2 on plus minus 1 to the n, there exists a distribution. Wait. Okay, yeah, there's a distribution on plus minus 1 to the n, efficiently sampleable, just like before, such that expectation with respect to this distribution, so this rounded distribution, is at least 1 over C of good. Yeah, that's what I'll prove. So this is just saying that we can get an order log n approximation to this quadratic optimization problem for diagonal less matrices B. Okay. Good. By the way, one thing I want you to notice, it's already present in the way we write theorem statements here. When we round, we prove a theorem that somehow, says that for every pseudo distribution mu, we can actually construct some rounded distribution that extracts some good fraction of its value. And we prove this result for all possible distributions mu. We just apply it to, the distribution that the pseudo distribution that optimizes the relevant quadratic function. So I guess the point I'm trying to make is that we don't use the optimality of the pseudo distribution. We don't use the fact that mu somehow, was chosen to be a best possible pseudo distribution in terms of maximizing twiddle E mu of Fg in the rounding. Our rounding analysis works for every pseudo distribution. Okay. And so this is kind of important because even though it doesn't happen often, there are rounding algorithms that do need to exploit that you're working with optimal solutions to certain convex relaxations. The stuff that we are doing is not doing that at all. And actually, if I remember correctly, we will never do it. I guess maybe we will do it once or twice in the middle of this class, middle of this course. We'll see one or two examples, I think, where optimality is important. But most of our rounding algorithms will really work for all pseudo distributions. Very good. So let's prove this. So as we saw, from one of the propositions we proved, it's enough to, just round the given pseudo distribution to, some vector, some distribution on the solid cube. Because once I have a distribution over the solid cube, I can compute, I can get a distribution on the corners of the hypercube by just this, randomized rounding that we did to construct y hat from y. Okay, so that's what we'll do. We'll basically focus on this goal, and it's going to be like a really simple rounding. So how would it work? So the idea is this, right? Let's look at this. So here's a rounding algorithm. So choose G to be what we are super duper familiar with now, Gaussian with covariance equal to the second moment of the pseudo distribution. And now, ideally we would have loved if this vector G has coordinates that lives inside the solid hypercube plus minus 1 to the n, because then we are done, right? Then we could just simply output this Gaussian itself. And in fact, we can even convert it into a point on the hypercube. And so if Gi were, small, let's say, for whatever reason, if you could prove that, these take no larger values than some big constant C, then you'll get, in fact, a 1 over C approximation, immediately. Of course, it's actually very simple to prove that, actually, maybe not so hard to prove that, if the diagonals of this E twiddle mu XX transpose are 1, then there's going to be a coordinate of G, which is going to be quite large. In fact, it's going to be square root log n large up to constants. So we can't quite hope that this Gaussian will work. But then that's just a very natural idea, right? Just scale Gaussian down. Right? Okay, G is not inside the hypercube, just scale it down. Bring it inside the hypercube by scaling it down. And hope for the best, right? And so that's the algorithm we analyze. Okay, it's a very simple algorithm. There's only 1 or 2 details that I'm not even sure I'll do it in full. So, the main observation is, and this you can prove using simple Hovding inequality and, a union bound, is that, probability that there exists an I such that Gi is bigger than, some, let's say, whatever, 10 root log n is at most, 1 over n square. And this is quite simple. This just uses the fact that, probability that a Gaussian with mean 0 and, variance 1 takes a value which is bigger than t is, e to the minus t squared over 2. This is the sub-Gaussianity property up to constants here. I think it might be just 2, if I remember correctly. And then, just apply this simple, Gaussian tail inequality with t equals some constant times root log n. Okay, so it's a very simple proof. And then you do a union bound, of course, on all possible n coordinates. Good. So this is not so hard. We can kind of do that. And so, we are saying that, with so, this implies that, with probability at least 1 minus some 1 over n square, we can kind of assume that all the GIs are, small. And so now, I can take the following vectors. So, choose V equals GI by 10 root log n. Okay, just scale it down. Then, with high probability over the choice of the Gaussian G, this vector, so, then what do we know? Then with probability at least 1 minus 1 over n square, V lives in the solid hypercube. So that's good. We wanted to round to a vector in the solid hypercube, and it seems like we'll get that with, all with some, except with some very tiny probability. So that's good. And so now, let's understand what happens to the quadratic form. Well, V transposed BV, conditioned on all GIs being whatever, at most 10 root log n, equals expectation of G transposed BG conditioned on GI at most 10 root log n. So if the Gaussian vector had coordinates which are upper bounded by some big constant times root log n, then, certainly, oh, sorry, I guess I forgot to write this one here. So this is just the scaling, right? Like if I scaled every Gaussian by 10 root log n, then, I get 1 over 100 log n as a scaling. But the point is that, the conditional expectation of V transpose BV is going to be, some within some 1 over O of log n of the conditional expectation of, G transpose BG. So the only issue is how do I relate this to, so I must relate this to expectation of G transpose BG, right? Because that's what I'm trying to compare it to, right? That's what my goal is. Like that's my target value. And so, this is mostly, an exercise in making sure the errors track. So let me maybe describe the final rounding algorithm and only sketch how this works instead of doing it in detail. So remember that, this rounding that we kind of were suggesting here, it doesn't always produce a vector in plus minus 1 to the n. And so one way to analyze what happens in expectation is to really give a rounding, that, always produces a vector in plus minus 1 to the n, even with with probability 1 instead of probability only 1 minus 1 over n square. So what we'll do is we'll let, oh, sorry, I guess we'll say for every I, let x hat I equals gi over 10 root log n if gi is, small. And, now, there's some very tiny probability that gi actually has a large magnitude. In that case, we'll just set it to okay. Sounds legit. At least this time, I'm going to get a vector with probability 1 in the solid hypercube. Now, in some sense, it seems reasonable to expect that the bulk of the value, the objective value in expectation should come from, the case where x hat I, was really obtained by scaling down gi by 10 root log n. And in fact, that's what happens to be true. This is where you need to use the fact that the value was at least somewhat large. So you need to use that opt of v was at least somewhat large in the analysis, and you show that the error here can be small compared to this lower bound in the value of opt that you had. Okay, so let me maybe not do this in detail, but just say that can prove that e twiddle x hat I x hat j is gij over some 10 log n minus some error, let's call it delta ij, and can prove by using the lower bound of the opt that we proved that some bij delta ij some ij in expectation is tiny. So like you can prove that this is at most opt of b over whatever n square or something. Anyway, so this is where you will need the fact that opt of v is at least somewhat large. You just account for the error that you get from this tiny probability event. You prove that that can only amount to a very small contribution to the value, and then you're done. And so that's it. Okay, and so somehow this very simple algorithm was discovered at least 2 times. There's like a paragraph long proof of this in Magretski's paper, and there is a similar proof and applications to some problem called as correlation clustering in this Cherry-Worth paper. So it was discovered at least twice. And we just saw its idea is very simple. Just take a Gaussian and scale it so that it lives in the hypercube, and then just do this randomized rounding that we did. So we're going to take a break in like 2 minutes, but one thing I want to point out before we do that, this rounding that we just did is a very, very simple special case of something called as RPR square rounding. Okay. The name comes from somewhat different way that people used to view semi-definite programming roundings. So like this P stands for projection and things like that. But let's not worry about where the name comes from. It's the following style of rounding solutions to degree 2 pseudo distributions. So in RPR square rounding in general, and I'll tell you why I'm telling you about this in a second. But what you do in general is you select a Gaussian, or actually, you get this solution, twiddle mu xx transposed. Then in step 2, you modify the solution somehow. We'll see one more example of what kind of modification we might want to do. But, for example, here, we modified by scaling down the covariance matrix. Right, like we scale down the vector, but that equivalently that scales down the covariance matrix. So there is like a step which modifies the PSD matrix that you get from the pseudo distribution. So let's just call it this modify step, and then the third step is to do randomized rounding. Right, there is like a in between step which is like sample a Gaussian from modified E twiddle mu xx transposed, and then good, and then you scale G to put it in the solid hypercube, and then do randomized rounding. I feel like one of the steps should not have been there, but doesn't matter. But basically, this whole program where you take an SDP solution or, the pseudo distribution, you modify it somewhat, choose a Gaussian, scale it, and then do randomized rounding. This simple thing that we just did is actually, goes by the name of RPR square rounding. I didn't exactly describe what kind of modifications are allowed, but basically, in this paper of Feige and Langberg, who actually proposed this style of roundings, they gave like a very specific kind of modification that were allowed. Again, not important for us. The reason I'm telling this to you, I'm like discussing this RPR square, is because last time I mentioned that Gomans-Williamson rounding for max cut is not optimal. When you when you think of graphs where the optimal value is far from this critical constant at which you get 0.878 approximation from Gomez-Williamson. And so you can ask, okay, what's the rounding that beats Gomez-Williamson rounding for these graphs, for the graphs for which the optimal value is far from this precise constant that corresponds to rho equals minus 0.69 or whatever. It turns out that the rounding is inexplicit in some sense. Like, it's not a very fixed specific procedure that I can describe to you. What is known and proven is that the optimal rounding is the best amongst this class of RPR square roundings. So it turns out that the best there is okay. So I guess I'm not sure if I'm super understandable. So let me maybe write it down. Saying suppose you want the best possible rounding for the max cut problem, then what you can do is just search over all possible RPR square roundings and output whichever gives you the maximum value. And so what is known is that whatever is the best constant you can prove in the certificate theorem, like whatever is the C that appears in opt over C minus F sub G having a degree 2 certificate, well, you can achieve it, you can prove that, and in fact you can get an algorithm to achieve that using just the best of all RPR square roundings. And depending on how much time we have, we'll see a proof of or at least a sketch of this in the next lecture when we discuss the unique games conjecture. Good. So let's take a break and come back and prove Grothendieck's inequality. So we'll reconvene at 5:50. So let's go. Let's do I guess one of the super fun parts of this lecture. And this is as I said earlier, this is still about this problem of optimizing X transpose BX over the hypercube, but this time we want to assume some structure in the support of B. Okay. And so like specifically the structure will assume well, actually it's not just structure in B, but structure in support of B. And remember, support is the set of all pairs for which Bij is non-zero. So in general, it's a complete graph, but when it's a non-trivial graph, we actually can say something more. I'll actually quote a result at the end, which basically gives something for all graphs. But right now, I want to prove something to you for bipartite graphs. So in particular, we want to look at the case where, let's say, support of B is bipartite. Support of B is bipartite. So what does that mean? How does a matrix B look like? Well, we already said the diagonals are 0. And if the graph is bipartite, then for any row, any vertex can only have edges to vertices on the other side of the bipartition. So let's think of n like n being even. So let's say in fact we have a 2n by 2n matrix. This balance is not needed. It just like saves me notation. And then the matrix must look like some non-zero matrix here, some non-zero matrix here, and these two blocks must be 0. These are of length n each. That's how the matrix B must look like, right? So if we now divide the Boolean vector in 2n dimensions into, let's say, 2 vectors of dimension n each, then notice that the quadratic form, so let's call this matrix B prime for now. I'm going to make it B in a second. Then XY transpose B XY just equals X transpose B prime Y twice. Well, this should be, one of them should be transposed. Let's make this transposed. Okay. The point is that, only these off diagonal blocks contribute. So equivalently, this is the problem. So, and this is the formulation I'm going to use because it saves me notation. So equivalently, we can think of B as the n by n matrix. B is going to be an arbitrary n by n matrix. And the goal is to maximize over all pairs of vectors in plus minus 1 to the n, the bilinear form X transpose By. Okay. And, I just explained to you this transformation where, in some sense, this is equivalent to the problem of, maximizing X transpose By when the support of B is a bipartite graph, and actually a balanced bipartite graph. Okay. Even like, if this transformation was not like 100% clear to you, or you're like still, latched onto it, forget about it. You can just like make this as our goal for now. So, that's the problem we'll think of. So, in some sense, the point is that so far we had to somehow use the same vector on both sides. So we're looking at quadratic optimization, quadratic form optimization. But this time, in this bipartite version, we get to somehow, have two different vectors, on each side of B. And we want to see what we can do in this context. But before I tell you what we can do and how we can do it, I'm going to tell you why we should do it. Why is this problem so important? Why should I care about this bipartite case? It just seems like some weird assumption, right? So actually, this quantity is an extremely important quantity, and the historical order of discovering all these results is completely opposite. Like this quantity was way more studied way more in detail in functional analysis, etc. For reasons so I'll tell you the reason, but the reason is that it basically captures a very general class of operator norms. Okay, so let's maybe talk about those. Now, when we usually refer to the operator norm of a matrix, we usually mean the following quantity. So this is the usual operator norm. We say it's the max over all unit vectors of the length of A applied to X. Okay, this is the operator norm of the matrix A, or at least this is the usual operator norm of the matrix A that we write with like a subscript 2 at the bottom. But actually, this is one of a whole sequence of operator norms that you can define. In general, you can define the following class of operator norms of A. You can, so let's say that you have so notation to use. Oh, I guess just use this for now. So here is like a more general definition of an operator norm of A. It's the infimum of all C such that AX is at most CX for all X in Rn. So, basically take the smallest C for which, this inequality holds. And the reason I'm saying this more general is because I have not fixed the choice of the norms on the two sides of this inequality. So in general, I can choose some norm to measure the length of the input vector X, and I can use some other norm to measure the length of, the output vector AX. Each choice of the norm on the input and the output gives you one new, operator norm of A. And in particular, we can define the following operator norm. It's called A infinity to 1. So you basically, the first thingy denotes how you are measuring the norm of the input vector. And the second thing it denotes the norm of the output vector, or the norm that you're going to use to measure the length of the output vector. And so in particular, this means max over all X non-zero, AX, the one norm, the infinity norm of X. Remember, I don't know if you don't recall, then, the one norm of a vector Y is simply, the sum of the absolute values of its entries. We are looking at finite dimensional vectors here. and the infinity norm is just, the max magnitude of any coordinate. Okay, so just to recall. And this particular infinity to 1 norm in some sense is like, um, the maximum that you can, the maximum norm that you can have if you are going to choose LP norms to measure the lengths of both input and output vectors. And the reason is simply that, if you had, let's say, instead of 1, you wanted to choose some LP norm here, and instead of infinity, you wanted to choose, LQ norm here, then over all P and Q, which are at least 1 and at most infinity, the worst, like the maximum, this norm is maximized, when you choose 1 norm here and infinity norm, in the bottom. And it's not so hard to see. It's just because, infinity norm is smaller than all other LP norms of X, and 1 norm is larger than all other norms of AX. So it's a very simple observation. And so in particular, if you can come up with, upper bounds on infinity to 1 norm of A, it's a way to, upper bound all possible operator norms, all possible LP operator norms of A. And so you can imagine that this kind of quantities would be relevant if you're doing functional analysis. And that's how, in fact, that's how I imagine Grothendieck was interested, in these quantities. So now what I want to observe for you is that this quantity A infinity to 1 is actually, exactly this bilinear optimization problem we saw. And this has a very simple it's a very simple observation. The observation is that if I fix so let's write it down as AX inner product Y. And now if I fix X, which means I fix AX, then there is a particular choice of Y that works. Simply, choose yi is to be the sign of, the vector, the coordinates of the vector ax, right? So given x, you perfectly know what y that will maximize. And in that case, the maximizer is simply the 1 norm of ax. So, for any fixed x, maximum of this is really the 1 norm of ax. And so now you see, like I'm optimizing with x in the hypercube. So the infinity norm is 1. So you can see why this in fact is computing. This is computing the infinity to 1 operator norm of A is basically just the solution, the optimum value of this bilinear optimization problem with the hypercube. And so in particular, I guess that's the reason that this quantity is super important in functional analysis. And what we're going to study now is algorithmic ways to compute approximations of it. Okay, very good. So here's a theorem. There exists a constant. Let's call it K sub G, and G stands here for not the graph, but Grothendieck. So there is like a fixed constant called Grothendieck's constant, such that Kg opt of B minus F, just explicitly write it, I guess, X transpose BY has a degree to SOS certificate. And there is like a rounding version, which I won't write down. But basically it means that I can find some X hat such that X hat transpose BX hat in expectation is at least 1 over K sub G of opt of B. Very good. And I think I said this at the beginning of the lecture, but we actually do not know the value of Kg. So do not know what Kg is. I think the best bounds we know on this are that Kg is between pi over 2 and and in a second, I'll explain to you why I'm making this a strict inequality. So we know like some reasonably tight bounds on K sub G, but we don't know a sharp bound. We don't know the exact bound. So today, what I'm going to prove to you is, today I'm going to prove to you, the inequality with this as the value. And so, we're gonna call this Crevine's constant. In fact, the proof I'm going to present to you will be the algorithmic version of like super duper elegant proof that Crevine came up with. So, as the name suggests, the first proof of this was by Grothendieck, but it was it wasn't explicit in a certain sense that allowed algorithms to somehow replicate it. But Crevine's proof is like extremely nice. It kind of works in the framework we built in the earlier part of the lecture today. And it's very simple, very short, very elegant, and it gives a proof of Grothendieck's inequality with some constant. In fact, that constant turns out to be this exact constant. So it's, by the way, like better than what we proved for PSD matrices because of this natural logarithm of 1 plus root 2 appearing in a denominator. It's like tinier than pi over root 2, pi over 2. And in fact, when Crevine proved this in 77, he conjectured that this is tight. And let's see, did I note down the year? Oh yeah, I did. So in 2011, Braverman, Makarichev, another Makarichev, and I think a Safnauer, in 2011, they proved that it's not tight. So they refuted Crevine's conjecture. And so, you might ask, well, what's the constant they prove? So they prove something which is like pi over 2 times ln of 1 over 1 plus root 2 minus 0.000000000000001. And I'm not sure if I, put in enough zeros there. Basically, they show that there is some fixed constant which is tinier than this value on the right here, which is also an upper bound in K sub G. So in particular, this is certainly not tight. And the reason why, in some sense, the reason why their proof gives us this tiny improvement is because the proof really works, in the way that Raj was asking at the end of the last class. So at the end of the last class, Raj was suggesting, hey, this Gormans-Williamson rounding is really tight when rho, this EGI-GJ ratio is like minus 0.69. So, in some sense, you can beat Gormans, you can hope to beat Gormans-Williamson by doing just the following, right? Do something very specific that only works when, this average of rho over the pairs that appear as edges is like minus 0.69. Like do something just there, like nudge the ratio when rho is like close to that critical value. And everywhere else, GW rounding itself beats 0.878 anyway. So this would be a way to prove that 0.878 is not tight. So we don't actually know such a proof for max cut. In fact, we expect there isn't. More about that in the next lecture. But actually, that strategy works here. So the rounding that we do today, basically what Braverman, Makarichev, and Naur showed is that they found out like the tight spot for it, and they showed that there is something else you can do there that nudges it off the tight spot. Like you can do something better when this rounding of ours is going to be tight. And so clearly, it's going to be, the constant is going to be better than whatever this number is here. It requires some work because you're trying to show that there is an absolute constant gap between this right-hand side bound and, and K sub G. So it's not just a matter of, perturbing and getting some little of one improvement. It's a non-trivial improvement, but you can still hope to do it by like nudging the solution of this critical SDP solution, whatever. Anywho, that's like fun information about how this proof works. Let's go ahead and prove this theorem. And in fact, while proving it, we'll give a new proof, or at least we'll give the Crevine's proof of just the existential fact, which is like a very important functional analytic fact. In particular, it proves that A infinity to 1 can be computed by SDP, with an O of 1 approximation factor. Good. So let's see. So let me give you the rounding. It's gonna look a little bit weird, but I'll explain to you and motivate it in a little bit. Okay. So let's say let's say that M is tilde E mu XX transposed. Okay. So far, and like we can always assume, as we have been doing throughout this lecture, that the mean is 0. Okay. Now, what we did in the first two parts, the first two examples we saw today was like simply take a Gaussian with this M as the covariance matrix and do something with it, right? Like scale it or take the sign of it or something. We're not going to do that now. What Krivine is going to do is, he's going to modify M before, running this sign rounding procedure. So the rounding is going to look like, compute some M prime, then compute, sign of a Gaussian with respect, Gaussian with M prime as a covariance. That's how the structure of the rounding looks like. So let me describe this M prime to you. So let M prime equal, don't be scared about hyperbolic signs. I don't know when was the last time you saw hyperbolic signs in your life. But they're going to appear for us here, and they're going to appear here for a very good reason, which I'll explain to you in a second. But hyperbolic sign is some function. It's a function of one variable. We're going to apply it entry-wise. So remember our notation, we're going to apply it entry-wise to a scaling of the second moment. So remember our solution has X and Y. So, I'm going to look at the matrix of X concatenated with Y, and it's out product with itself in the expectation. So I have like a 2n by 2n matrix, if you will. And so, on the diagonal blocks, I have hyperbolic signs applied entry-wise to some scaling of, twiddle E of XX transpose and YY transposed. And then on the off diagonals, I'm going to have the usual signs. Okay, again, wrong brackets. So this is the entry-wise operation that we studied earlier. All right. So a priori, it's not even clear why, this matrix has diagonals 1, but we're going to ensure eventually when I choose this constant small c in here, we're going to ensure that the diagonals of M prime are in fact 1. So we'll ensure that has diagonals 1. And, just to in fact make my, reveal all my cards here, like C, in fact, we're going to choose as this weird quantity that appeared in the denominator in Krivine's constant. But don't worry about it too much. It's going to be a fixed constant, and I'll give you how it's chosen in a second. But once, I modified this matrix, so I took M and I modified this matrix to get like a new matrix. I haven't proven to you why this is positive semi-definite, why it has diagonals 1. I'll do that in a second. So, M prime is actually going to be PSD. I'm going to prove it to you. Then, you just choose, this 2n dimensional vector G comma H with M prime as the covariance. And then, you output, this part is, we are familiar with it now, sine of G as X and sine of H as Y hat. Good, that's the rounding. It looks weird, and I have several claims to justify to you, but basically, at the heart of it, it looks just like take M, modify it to get like a different PSD matrix which has diagonals 1. Then, do sign rounding with a Gaussian, just basically do the usual Gaussian rounding on it, like the same thing that we did, in Gomez-Williamson, and also, for rounding PSD quadratic forms in the first part of the lecture today. Okay. So except this modification step, everything is the same. Okay. And I'll explain this.
Quick question. It's not immediately clear that M prime is PSD, right? Because you're applying different functions.
Sure. Yeah. Yeah, that's what I said. Like I have to justify multiple claims to you. In particular, I haven't proven to you that M prime is PSD right now, but I will prove that to you. And then, M prime is like a legit covariance matrix. So I can choose G comma H from this Gaussian distribution. Then I can take their signs and round. Okay, good. So that's how the rounding will look like. So now, okay, let's say it's a good thing to do. Okay, so let me make a claim. So, there are multiple claims for me to justify, but let me make yet another claim. And the main claim, so let's note down all that I need to prove to you. M prime is PSD. Diagonals of M prime are 1 and 3. In fact, this is the reason I'm choosing M prime in this weird way. If I look at the off diagonal part of the original pseudo distribution, then it's going to be a scaling of. So if I just wanted GH transposed here, like if I just wanted so let me write it down here. This is not going to be the right thing. I'm going to modify it in a second. But notice, like if I just wanted the matrix M prime to satisfy this, then M prime should in fact have been M, right? Like if I literally if I didn't modify M, I chose G comma H as Gaussians with M as the covariance, then I get this equality for free. In fact, with K equals 1. Okay? But that's not what I'm asking for. I'm going to ask for the following fact. So I'm asking that the distribution of the Boolean rounded vectors have covariance, which is a scaling of this off diagonal part of the original pseudo distribution. Okay, so notice that this is a Boolean distribution. While here, it's a pseudo distribution. So we are basically matching these off diagonal parts of the pseudo distribution up to some fixed constant K. Okay. Well, once you do that, once this main claim is true, which I'll prove it in a second, proof of theorem using main claim. So assuming this main claim, the proof is actually very easy. So let's, look at this quantity. This is the value of the bilinear optimization problem on the pseudo distribution that we compute. Right? This, if you have a pseudo distribution over the concatenation of X and Y, then that's the value I get. Right? Well, this equals, just by rearranging, the trace of the matrix E mu of X5 transposed times B, or B times E mu of X5 transposed. Okay? Actually, is there anyone who needs me to prove this equality here? So, so let me just do it anyway. So this, remember, is Bi Xi Yj expectation. And if you take like trace product of two matrices C and D, then actually it just equals sum ij Cij times Dij. And so, this right hand side actually just equals sum over Ij of Bij twiddle mu of Xi Yj. Good. So, they are equal because they're literally the same expressions. Anyhow, so in case, there was, this was like some sticking point, hopefully we've cleared it away. So this equality holds. And then, if we use third part of the main claim here, then we know that this in fact equals trace of B expectation GH sine of G sine of H transposed. And we need to have this scaling constant K. And in particular, equals K times the rounded value And so you see, we are done because what have we proven? We have proven that, the rounded value is at least 1 over k of this, pseudo distributions value. Okay. So I guess all I'm saying is that, that all the action is really in this proving this main claim. Okay. So let's prove it. Okay. So let's actually do it in reverse so that we discover why we are choosing the modification in the way we are doing. Okay. So if I have any, so let's try to understand what this M prime should have been. So M prime was the covariance of these Gaussians G and H, right? So recall that expectation GH sine of G sine of H transposed. So we proved in the first part of the lecture that this in fact equals so actually again it should be square brackets. So we stated it there for each entry, but I'm just stating it as this arc sine function applied entry-wise to the matrix E, G, H transposed. So it's the same thing that we did earlier. We say, like the correlation between these rounded, the sine rounded vectors actually is given by, the arc sine 2 over pi times arc sine applied to entry-wise to, the Gaussian correlations. So this is what we remember, right? So now, what was our goal? We want to somehow, choose this matrix, the covariance, like this is part of the off-diagonal part of the covariance matrix of the Gaussian G comma H. We want to choose it in a way so that this is a scaling of the pseudo distributions value, right? Like we need to choose it in a way, that this, arc sine applied to EGH transposed looks like e twiddle mu of xy transposed, right? So I should somehow, so this was part of M. I must modify M in a way so that when after modification I apply the arc sine function pointwise, then I in fact get, e twiddle mu of xy transpose up to some constants, up to some scaling. So now you see what I should choose, right? There's only one choice. Then must choose EGH transposed to be sine applied to C times some scaling of e twiddle mu of xy transposed, right? Like there are really no two options here. I have this arc sine thingy applied, outside. So I first apply the sine function entry-wise to this off-diagonal pseudo-distribution matrix up to some scaling. We'll see why we need the scaling in a bit. We haven't justified that yet. But now, if you apply 2 over pi arc sine entry-wise to sine applied entry-wise to this matrix, then you see you recovered what we wanted, right? Then you do recover what we wanted. We do get, e twiddle mu xy transpose to be the covariance of, this rounded distribution, the off-diagonal part of the rounded distribution up to some scaling. So this is great. We kind of have derived that it better be that this M prime. So what have we derived? So, we are trying to discover the structure of M prime. So we kind of know, so we don't know what's happening to these diagonal blocks. We haven't, settled on it, but we know the off diagonal blocks. We know that they definitely have to look like this. Right? Now remember that we started with M. So M looks like this. So M has diagonal blocks, XX transposed, YY transposed, YX transposed, and XY transposed. Now, one thing you might guess, we did this at the beginning of the lecture. So you might guess that, if I just apply sine to all the diagonal blocks too, instead of just applying, so for my optimization problem surrounding to work in the natural way, I definitely need sine to be applied to the off diagonal blocks. Okay. you might, naturally think that, well, I might just apply its sign entry-wise to the whole matrix M. This was M, and hope for PSD-ness. But can someone tell me why this is a bad idea? Why can't I just take the diagonal blocks here to be signs of the diagonal parts of M? Feel free to unmute yourself and tell me why this is a bad choice.
The Taylor expansion has a negative coefficient.
Absolutely. This is not going to be a PSD matrix, right? Like the Taylor expansion, of sign has alternating positives and negatives. So sign of a PSD matrix has no reason to be PSD. So you can't quite do that. So now you see why this hyperbolic signs appear. So what we're going to show is that if you fix the off diagonals to be the sign function applied to a scaling of this expectations of yx transposed, if you choose hyperbolic signs here, then in fact, you can make this matrix PSD. So that weird choice of hyperbolic signs in a diagonal is simply to make, so the off diagonal choice was like, we were really, in some sense, if we want to analyze it in a natural way, we had no option but to set the off diagonals as sign function applied pointwise. And then, we have to set the diagonal so that the matrix becomes PSD, but we can't quite use the sign function. So we'll use the hyperbolic sign function. That seems like a very bad argument. Why should we use hyperbolic sign? So here is the key fact. If sign function, let's say in the interval -1 and 1, has the Taylor expansion so suppose sine of t equals t to the k, then here's the cool fact. The hyperbolic signs Taylor coefficients are absolute values of the coefficients in the Taylor series of the sine function. This is the key fact that, is dictating why we should have the hyperbolic signs on the diagonal. Okay. So now, now you at least see some reason behind why these weird functions are appearing, and especially entry wise. So now, let's demystify why this actually works and why this connection between the Taylor series coefficients of the sine function and the hyperbolic sine function, is useful. So, this M, so instead of writing all those things again, let me just call them M11, M12, M21, M22. That's how our matrix looks. Now, we want to rely on this lemma that we proved earlier using the should product theorem that, certain functions when applied to entry-wise to entries of a matrix, PSD matrix, preserve PSD-ness, right? So, so in particular, we were looking at, these, okay. So the basic building blocks of the function that we analyzed at the beginning were, like this polynomial functions, and in particular, like the monomial functions, like just taking powers of each of the entries, right? So let's consider the following function. Like let's consider the following operation. So let me maybe state it as a proposition. Suppose M is PSD, then so is okay. This fact is what we proved earlier, that if we apply the ith power function entry wise, then I'm going to get a PSD matrix. I'm just writing it, it's like a very cumbersome way of writing M to the I, right? I'm just applying it to each block separately. But the reason I'm doing it is because I also want to claim that even if I negate the off diagonals here, even then I get a PSD matrix. So who can tell me like a one-line proof of this? Okay, so it's like 6:30 p.m. Eastern time. So let me just we just, it's really simple. And I'm sure if I had asked you this question at 4:30 instead of 6:30, you all would have told me what's going on here. The observation is that, if I compute the quadratic form of this matrix on vector VW, then it's the same as the quadratic form, hopefully I got it right, of V minus W of the unnegated matrix. So there's basically a correspondence between quadratic forms, which means that, the quadratic forms of one are like one of them are non-negative if and only if the quadratic forms of the other are non-negative. Both are like symmetric Hermitian matrices. So, one is PSD if and only if the other is PSD. And we kind of know this is PSD, so we are done. Okay. So now we will use this cool proposition in the following way. So now you see that, in some sense, the point is that I can have sign coefficients on the off diagonals as long as I keep the absolute values of those coefficients on the diagonals while taking these polynomial sums. Okay. So corollary, for all polynomials, Px equals, let's say I equals 1 through, I don't know, let's say degree k, ai, x to the, let's call it t because we keep using x elsewhere. The following matrix is PSD. So, I just apply, let's call P plus to be the polynomial where the coefficients are absolute values. Then, I apply P plus to the diagonal blocks and apply P to the off diagonal blocks. If M is PSD, then so is this guy. Okay, makes sense. Again, feel free to stop me and ask questions. Like, I'm more or less, done with like maybe a couple observations now. So yeah, if you have any questions, feel free to stop me. So that's great. And so, just like we ignored analysis, or at least the details of the analysis earlier, we can extend this observation not just to polynomials, but to uniformly convergent Taylor series on the interval -1, 1. And so, can extend this to uniformly convergent Taylor series on any fixed interval, let's say -1, 1 for whatever reason. And so that gives us another corollary. So, using this fact that I claimed to you that the hyperbolic signs Taylor series coefficients are, just absolute values of the coefficients of the sine function. And actually, I'm again going to, by fiat, claim to you that over the interval -1, 1, both sine and the hyperbolic sign have uniformly convergent Taylor series. Therefore, this matrix is always positive semi-definite. Okay. Actually, let me plug in C there because this is true basically for all non-negative C. Okay, so that's great. The final thing is, how should I choose C? Well, now the only remaining constraint, that I still have to prove to you. That's the point number 1 in the main claim, which is that I must make the diagonals of this matrix take the value 1. Now, the matrix M had diagonals, which they were 1. And so now I must choose. So for part 1, must choose C so that the hyperbolic sign of C is 1, right? There's no other option for us We got to choose that because the diagonals of the matrix M are 1. So we must choose a scaling C so that the hyperbolic sign at C evaluates to 1. And yet another claim by Fiat, the C that you need to choose just to check that all of you are awake at 6:35 p.m. Can someone tell me what that C needs to be? It's basically a constant that we wrote down in the theorem statement earlier. Feel free to unmute yourself. Shout it from the rooftops.
Isn't it the one you said, like 1 over log 1 plus square root
Yeah,
2?
absolutely. That's exactly what it needs to be. I am not the factorial. I mean, it's my exclamation mark here. Okay, so that's it. That's the proof of Grothendieck's. That's basically Krevin's proof of Grothendieck's inequality. If you just collect this proof together, then the coefficient you get. So this implies that k sub g is at most pi over 2, and then the c shows up. Actually, wait. This needs to be not 1 over. It needs to be 1 plus root 2. Sorry about that. But that's why it shows up in the denominator. That's why you get like a slightly better approximation than pi over 2. It's because hyperbolic sign is 1 at, takes the value 1 at, a natural log of 1 plus root 2. And I already told you that this is not tight. If we already know that k sub g is in fact strictly less than this Krevin's constant. Yeah, but that's not a very simple proof. At least, it's kind of a messy proof that analyzes when is this rounding tight and then does something better for those precise kinds of covariance matrices that arise from pseudo distributions for which this analysis is tight. Okay, so that's it. I guess that's all I had planned. I guess I didn't have material for the last 10 minutes, which means that we can actually discuss / take questions starting now.
So I was wondering, is there like a canonical combinatorial problem that corresponds to this like bipartite matrix quadratic form problem in the same way that max cut is like?
Good. It's a good question. The closest I can think of is the problem of approximating cut norms. So let me describe that to you. So, basically these problems, all of these problems, at least like this bilinear optimization problem is like computing a certain very natural norm, as I explained to you. It's like computing a certain operator norm of A. There's a different operator norm that also, slightly different operator norm that still turns out to be super important. And that's a cut norm of a matrix B. So, let's say you're given a matrix B in n by n. Then the cut norm of B, let's just maybe call it B cut, is maximum over all choices of subsets I in S, J in T, B I J. I guess I called it combinatorial because there are cuts going on. I don't know if that's convincing enough for you, but it actually turns out that A infinity to 1 that we saw before is basically a constant factor approximation to the cut norm. So now I forget which way the inequality goes, but I think, let me just make a claim which is definitely true, but slightly vague, is, a factor 4. So, is within a factor 4 of, cut norm of the same matrix. So in particular, you can approximate cut norms within, fixed constant factor. Yeah. Actually, I just realized that I forgot to tell you one more thing. It's not a theorem, it's a story. So I like this part of the lecture was, I phrased it as exploiting some structure in the support of B. But it's not a very meaningful thing to do if the only example I show you are complete graph and bipartite graphs. So in general, this would be a relevant thing to do if I can somehow, characterize what the approximation factors we can get, etc., in terms of, the support structure of the graph. And so it turns out that, in this very nice paper of Alon, Makarichev, and Makarichev, all this action, by the way, is happening in, early to mid 2000s. So, this is like 15-year-old stuff mostly. And so, I guess, again, I don't remember the date, but this might be 2005 or 6 or something. These are the people who realize that you can somehow, think of growth intake as a special case of this, quadratic optimization problem where the graph is bipartite. And then they ask the natural question, what happens if I took, a support to be, some arbitrary graph G? How do I somehow, can I say something about, the SOS certificates and in particular approximation algorithms in terms of properties of G? And they did. Here's a very neat theorem that comes out of the work. The best approximation to X transpose BX. So still quadratic optimization, X in plus minus 1 to the N, X transpose BX over all matrices B that have support graph G is between, so let's say I get that right. I think it is between the, well, it's certainly at most the chromatic number of the graph G and what's the lower bound? I guess I forget the lower bound. It's supposed to be, let's see, can I guess maybe? I think it's supposed to be the independence number, or let's say maybe just the click number. Oh, I guess that makes sense. Okay. So I think, so I might be messing up some constant. So let's say theta of the click number and the chromatic number. So the best approximation that you can get is going to be at most the chromatic number of the graph G. So what's the chromatic number of the complete graph? Oh, I guess there is some log that I missed. Sorry. Seems like I'm sleepy too. Okay, that makes a lot more sense. So what's the chromatic number of the complete graph? Well, you certainly need n minus 1 colors because all possible edges are present. So this is telling you that, the ratio is, that you can definitely get an approximation algorithm that gives you a order log n or theta log n, approximation factor. But in general, if you take a graph which has like, a smaller, non-trivially smaller chromatic number, then in fact, this result of Alon Makarichev tells you that you can get a better approximation. And in particular, the best, the approximation that you can get is certainly log of the chromatic number of the support graph. And they also prove a lower bound saying that, this is related parameter of the graph that somehow, is at least something that you would have to lose when you try to approximate. And that happens with the click number, of the graph. A click number of the log of, log of the click number of the support graph. And so, this result is in some sense what justifies me calling the second case the bipartite case and the unrestricted case the complete graph case and so on. Like in general, in fact, it is indeed true that you can, get approximation factors which depend on like this very nice, simple, natural, parameters of the graph. And so, if you're interested in this kind of stuff, I highly recommend reading this paper. Actually, many of the papers I refer to today are like really, really nice to read. They're like, yeah, they're super fun to read. So I definitely recommend also reading Magretsky's paper. I'll post, these papers on our Didro so that, we have a record of them. Okay, yeah, that's something I had planned and I forgot, but glad I got to it. We can still take questions as usual.
So if you did not have logs, this looks suspiciously like low-wash theta.
Yeah, actually there is a, so I'm not mentioning it, but there's, I think, a better lower bound that you can do in terms of low wash theta function of the complement of G. And so, yeah, there is in fact a strong connection. That's in fact how that's how their proof works. It is connected to, this low wash theta function of the complement graph. So, this lower bound can be improved actually. Can be replaced by, this theta function. Let's see. Log of the theta function, no, log of the theta function of G complement, if I remember correctly. Yeah, up to constants. Lots of thetas, but this theta is different from this theta. This is Lowage's theta and this is my theta. Okay, more questions.
How is the lower bound on Kg proven?
Ah, good. Good question. One that I actually don't have an answer to right off the top. Yeah, I don't know, but I'll look it up and maybe post a blurb on Twitter about it. It's a good question. I mean, all of these lower bounds were proven by, so I'm not sure like the first proofs were like that, but for all the problems that we saw today, the lower bounds that we know were eventually proven using explicit matrices. So people like literally gave, here's the B you must use. And for this matrix, we're going to prove that, there is no certificate unless you lose this correct value of C. And so that's how you prove, this order log n approximation is tight for this diagonal-less optimization problem that we saw before. And I think that's also how you can prove that lower bound on this growth and D constant. But yeah, I don't know exactly what that construction is. So I'll look it up and post it on Didro again.